Welcome back everyone, my name is Vedram and this is where we do advanced time series analysis, deep forecasting. Alright, let's continue our journey for module number 5, machine learning for time series forecasting. In part 1, we reviewed the fundamental concepts of machine learning for time series forecasting. We saw that how we should transform a univariate time series dataset and prepare it for a supervised machine learning task. We also discussed the idea that how machine learnings are able to do multi-output forecasting as well as single output forecasting. Remember, in the previous module, we said that econometrics models by construction are not designed to be able to do multi-output forecasts at the same time. But we discussed it last time why machine learnings, not all of them, but some of the machine learning models are capable of doing that. Now, in this part 2, we're going to go over decision tree based models. The reason that I'm going to cover these models is that in practice, they work better when it comes to time series dataset. But this doesn't mean that at the end of the day, you cannot apply all different machine learning models to a time series data. The rules are pretty much the same. You're just going to change the engine. I will specifically cover these models, these decision tree based models, and I want to go walk you through over the intuition. What's the difference between a single decision tree, random forest, XGboost, Catboost, and LightGBM? What is fundamentally different between them, and why are they going to work for a time series dataset? So part 2, decision tree based models. What I'm going to do in the next few slides is to help you understand how a decision tree works for a time series regression task. I'm pretty sure that you're all familiar with the concept of decision trees when it comes to a classification task, but it's not quite clear how it works to a univariate time series task, right? So that's my goal, and hopefully you will have a better understanding at the end of this lecture. And then we're going to cover the fundamental questions when it comes to decision tree based models, right? There are 4 fundamental questions that we're going to cover. And we discussed that based on how you answer these questions, you're going to end up with different models. For example, you're going to end up with decision tree, random forest, XGboost, and etc. Okay, so that all depends on how we answer these questions. But before that, let me quickly review some terminology when it comes to the decision tree. Again, I assume that you have the background, so it's going to be a quick one. So what is root node? Root node is basically the first decision node at the top of the tree. So there's a decision criteria in it. If it is met, we go to the left. If it is false, we go to the right, or the other way around. It really doesn't matter. So this is the process of a splitting based on the decision criteria, and the first one is called root node. Then, for example, we go to the left side, there's another decision node. Based on that decision, we split the data. When we go to the right, the same story. We split the data based on that decision criteria, and etc. etc. So we can continue this process of splitting until there is some stopping criteria met. For example, we want to have a minimum number of observations in each terminal node or leaf node, right? And by the way, this last nodes that we have, we call them leaf node. Another important concept is the concept of depth of a tree or level. So depth, because I'm going to use this in the Python part as well. So we will discuss the idea of depth or level of the tree. It's pretty straightforward. It's the longest path from the root node to the leaf node or terminal node, and you're going to count the levels, right? So if I go, for example, let me use another color. So we go from here all the way down to here. So this is going to be the longest path, right? How many levels do we have? 1, 2, 3. So the level of this decision tree is going to be 3. All right, now let's go back to the questions. What are they and why does it matter? So we're going to say, again, I'm going to review each of these each questions on a separate slides, but at a high level, this is what we're going to discuss. How to sample the data for splitting. And again, guys, I'm going to show you a time series example, a univariate time series example. So this is probably something that you haven't seen before. So how to sample the data for splitting, right? So this is an important question. And number 2, how to split those samples, what features and cutoffs to start with, right? So for example, in first node, should we start with feature 1, feature 2, feature 3? What is it, right? And what does those features mean for a univariate time series? And number three, how we can grow a tree. Basically how we go down the tree, how we can make it bushier, how we grow it. And finally, if we have some sort of ensemble or boosting methods, how we're going to combine those trees. So these 4 questions are going to help us to understand the difference between decision tree, random forest, XGboost, Catboost, and LightGBM. Let's go over a very simple decision tree model, and I want to walk you through the intuition when it comes to how we can apply that decision tree to a univariate time series data. So let's stick to our very simple, well-behaved time series data, which is our airline passenger data set. So let me go ahead and use my cursor. So this is our airline passenger data set. It's a monthly data, and as you can see, there's a clear trend, there's clear seasonality. And now we want to apply a decision tree model to that. So remember, this data set looks like this. You have YT, something like this, right? So basically, this is your YT, right? So your first task was to transform it from a univariate time series data to a supervised machine learning data frame, right? So how do we do that? For visualization purposes, I'm going to only use 2 lags, right? So I'm going to say, let's do lag 1 and lag 2. So in this case, we're going to have YT minus 1 and YT minus 2, right? Guys, it really doesn't matter. It's just a subscript. You can think of it as YT plus 1, YT and YT minus 1, or you can say this is a target variable YT, and this is your lag 1, lag 2. So this is going to be your feature X, and this is going to be your target variable Y. So that was step number 1, how to transform the data from a univariate to a machine learning data set, supervised. Okay, so these are the observations. Month 1, 112. I think these are number of passengers, 112, and then 118. I think these are in thousands, and 132, and etc., and we have the features, right? So now let's go ahead and visualize it in 2 dimension and color code it. So this is my feature 1. I'm going to label it as X1 because you're most probably familiar with this notation, X1, X2, and the classification task for decision tree, but this is different, right? This is, we're using a single time series, and then we're using lag 1, lag 2 as features, and we're plotting them, right? So basically, for example, we can have this observation. So what is this observation? So we have 118, I don't know, let's find 118 somewhere, so maybe here, and then the 112, so this is 112. So this is this observation, right? And you get the idea. We're going to plot it for all the 144 observations in the data set. So let me go ahead and clear things out here if I can. Well, never mind. Okay, so then I want you to focus on this data set, focus on this graph, right? What do we have? We have lag 1, lag 2 as features, and it is color coded. So what are the colors? The colors are the number of passengers, monthly passengers, right? The lighter they are, the higher the number, and the darker they are, the lower the number. So for example, 132 for this observation, so that's the color. The color is kind of darker. So I don't know, let's do it blue, right? So I'm here. So hopefully these dots make sense now, how we can go from something like this on the left to something like this on the right. Now, if I show you something like this and say, hey, go ahead and use a simple decision tree to make predictions, what do you do? So let's say, imagine you have a decision tree like this, and I'm going to go with the simplest decision tree with 1 level, and we have basically, the depth is equal to 1. Let's show with small letter d. So this is depth is equal to 1. This is the simplest decision tree. So as you can see, there's a split, right? So here's the split, and we have a criteria here. And then the split is, should we start with lag 1 or lag 2? And if you start with lag 1, where should we put the split? Is it here? Is it here? Where is it, right? I want you to pause the video and think about it. Which feature should we start with? Is it lag 1, lag 2? And if we start from lag 1, for example, where should we put the split, right? So hopefully you are looking at your target variable. What is target? These colors. So I'm going to, let's say, start with lag 1, and I'm going to put this line somewhere. I don't know. I'm going to put it right here, maybe. Again, this is just a speculative, right? Why am I doing that? The reason is that all these dots on the left-hand side are darker. All these dots on the right-hand side are darker, right? So this means that then I'm going to go ahead and report 1 number for the region number for the left region. So let's call it region 1, R1. This is R2. This is your R1, this is your R2, just for example, right? And what is a prediction for R1? Basically the average number of so this I belongs to R1, right? The average of the target variable, right? So whatever those numbers. So for example, those numbers, let's say those numbers are higher. I don't know, maybe that number is in a scale of 200-ish. Okay. Sorry, those numbers are smaller or 200-ish. What about these ones? These numbers are higher for in R2. So the average of all those dots, I don't know, maybe they are in a scale of 400-ish. Again, these are super simple numbers. So this is your decision tree, and we're using a simple decision tree with one level, depth is equal to 1, for prediction. And now, if I want to go back to the data set, how does it look like on the univariate time series data set? Remember, we're going to say, I don't know, for some observations, the model is most probably is going to project 200-ish. No, let's see. This is 200. Maybe for these ones, it's going to predict 400. So this is what the model is going to do, right? So basically, this is your regression line. This is your decision. This is your time series regression line, right? And how it's going to look. These are the predictions. Obviously, it's doing an awful job, but the reason is that we only have we're predicting that everything is going to be two numbers, either 200 or 400. How we can increase that? So obviously, if you make this tree a lot bushier, then you'll get more levels, right? And this is exactly what we're going to do in next slide. So I'm going to show you how we can do these things in Python. And by the way, the Python code is available on the GitHub. It's called Decision Trees Intuition. And I'll walk you through that Python code quickly at the end of this lecture. So here are the actual numbers. I used Python and tried to work with a simple decision tree with depth is equal to 2. So again, here depth is equal to 2. And use Python to come up with these cutoffs, right? And it seems that, look at that, it seems that we are starting with lag 1. Remember, this is your one feature, and this is your feature number 2. And look at the first split. It says if lag 1 is less than 297, so 297 is here, right? If it is less than 297, go to the left. So, and then what is the next criteria? Again, lag 1 if it is less than 214. So we're going to start with lag 1 again. Now this is 214. Otherwise, we go to the right, and again, the decision tree says that, again, pick lag 1 and 418. So 418. Why is it always lag 1? Again, because this was the most important feature for this data set. I have two features, lag 1, lag 2. And it seems that as we go down the tree, it seems that lag 1 was the most relevant. So that's why the algorithm picked lag 1. I'm going to talk about what is the criteria, what is the optimization process behind the scene, and then you should hopefully have a better understanding. But again, I hope that this makes sense now, right? If I go with a decision tree with depth is equal to 2, we are going to end up with 4 predictions, right? So this one, let me label them. Let me call them R1, R2, R3, R4. So this is your R1, R2, R3, R4. It could have been something like this, right? So just don't think that it has to always be horizontal in this example. All right. So for example, for R1, what is the value? These are the predictions value, right? The prediction value is 164. So where's 164 is coming from? If I take the average of these numbers, is 164. If I take the average of these numbers, what is the answer? 254. The average of these numbers, this is your R3, 356. Hopefully you're following, right? Where I'm picking those numbers. And for R4, the average of these numbers is 486. Now, this decision tree with depth is equal to 2 is predicting 4 numbers. Let's visualize it on our time series data on the next slide. There you go. So I want you to start by focusing on the left side graph, right? So this is where the max depth is equal to 2. This is what we saw the decision tree on the previous slide. And I told you that the predictions are going to be 4 numbers, right? And the first one was 164. So this level is 164. So for these observations, the answer is 164. These are the predictions, okay? So let me try to use another color as well. So, and then what was the second level? The second level was 254. So this is 254, 254, 254. You get the idea, okay? So this is the 254. The third one was in region 3 was 356. So this is 356. And now you get the idea how decision trees are actually making predictions. And finally, the last one, the fourth number was, let me check my slide, 486. So this is 486. And guys, pay attention. These are in-sample predictions or in the train set predictions. Obviously, this model is doing a horrible job because if I go ahead and calculate the root mean squared error, it's going to be crazy large. So for example, what I'm talking about this. For example, this is actual, this is prediction. So for that simple observation, the error is huge, right? So this is a large error. And if you go ahead and calculate the mean squared error overall, it's going to be, or root mean squared error is going to be very bad, right? But this was if your model was super simple. It was a decision tree with depth is equal to 2. What if we increase the depth to 10? And as you can see in the train set, it's gonna nail it, right? So if I increase it to 20, to 30, 40, whatever, if I make the tree a lot bushier, then because it's complex enough, basically it's going to memorize, it's going to learn everything in the train set, right? So we can probably get an RMSE or MSE close to 0 in the train set. So don't get super excited. I'll talk about the caveats. So this is in the train set. In the train set, a simple decision tree with a depth is equal to 10 is going to shine, right? And you might wonder, oh, wait a second, why don't we always use a decision tree? We make it bushier and for time series. The reason that we cannot do that, I'm going to discuss it at the end of this lecture by going through the Python part, is that we care about forecasting. We care about, test set performance, how this predictions look like in the future horizons. And as you're going to see, it's not going to perform well. So we have to do something about it. But for now, I just wanted you to get the intuition how decision tree regression works for a univariate time series data. And then how we can make a perfect fit in the train set. But the caveat is that in the test set, it's not as simple as this. We have to talk about the details. Now, with that simple example in mind, let's go over the 4 fundamental questions that we raised at the beginning of this lecture. So I'm going to start with this one: what features to start with and where to put the cutoff, right? So in order to answer that question, we need to see what features and cutoff is going to add the most information gain. So what do I mean by that? This means that which one, for a regression task, which one is going to reduce your cost function the most, right? So let me actually remind you what do we mean by these information gains. There's a function for that, right? So if it is a regression task, you can think of mean squared error. Obviously, you want to minimize it. If you want to think about classification task, we have seen error rate, entropy, or Gini index, right? So again, this is we're focusing on regression analysis, so I don't want to confuse you. So let's just focus on mean squared error. So this is going to be the criteria that controls how decision tree decides to split the data, right? So let's stick to that mean squared error for our very simple example. So what do we do? Imagine we have the entire data in one region. This is where we start, right? So this is the beginning of a tree. So we can go ahead and calculate the mean squared error. So mean squared error. So we can call it total mean squared error. Then you're going to go down the tree. You want to decide where to put the split. You say, okay, let's start with lag 1, and then create a criteria for that. Let's start with this red line and assume that this is 300, right? So 300. Now we're going to have 2 regions. So region 1, region 2. Again, just focus on the vertical red line. So region 1, region 2. What do we have here? We have mean squared error for region 1, mean squared error for region 2, right? The way that the computer does it, you're going to calculate a total mean squared error. So at here, we're going to say, okay, we have mean squared 1 plus mean squared 2, and it's going to compare it with the previous split. What was the error in the previous split? It was mean squared error, the blue one. Okay, and if it is smaller, it's going to go down the line. It's going to go down the tree. And the answer here is yes, so we're going to go down the tree. And then we keep doing this, right? So if I want to go one more level, right? So if I want to go one more level, then I have two more regions. So we're adding these two lines, you know, this one and this one. These are two new criteria, right? So maybe again L1 lag 1 less than 200 here. I'm rounding up numbers, and lag 1 here we can say less than 400, for example, right? And then we go to the left and right, and then at the end of the day, look at that, we have new R1, R2, R3, R4, and again we're going to calculate the summation of mean squared error for all those regions, right? So this is what we're doing. Mean squared, this is the mean squared error. Well, if you divide it by number of observation in each region, it's going to be mean squared error, but this one is the squared error, right? You get the idea. So, and we're going to have it for 4 regions, for example, here, going through 1 to 4 for, let's say, J. All right, and that's how it goes down the tree, right? It's going to make the splits, and then the idea is that, again, what feature to start with, where to put the cutoff. Put the cutoff in a place that is going to minimize these summations, right? So because if I go back to the red line, if I put the red line here, then I have one region on the left, one region on the right, region left, region right, right? And then the summation of the mean squared error for this cutoff is going to be a lot worse compared to the summation of the mean squared error for this cutoff. So that's why this cutoff is going to be the winner. Does that make sense? So this is how, and again, we have to try all, and the next natural question is that, okay, how many, no, where do you put the cutoffs, right? So for every single observations, you're going to consider a value, and the answer is yes. So this is the naive sampling method. Next question, we're going to talk about what is the sampling method, right? And as you can guess, the naive method is that go ahead and for every value, so hopefully you're seeing my cursor here, I'm here. For every value, consider a cutoff. And literally calculate all of those mean squared errors totals and then compare them with each other. Do the same for lag 2. And see between lag 1 and lag 2 which one is the best, and pick that one, and from the best one pick where you should put the cutoff. So that's how we answer question number 1. Let's move on to the next question, how we sample the data, right? Again, one method was just naive sampling. Obviously consider all the cutoffs, and there are some other alternatives as well. Great, now let's focus on the second question, how to sample the data for splitting. So there are 3 methods, one pre-sorted naive, second one histogram based, and third one GOSS, which is a gradient based one-sided sampling. So the pre-sorted naive, this is the most intuitive one. This is exactly what we did. Basically, we're going to sort all the data, and remember in the previous example we had lag 1. Let me try to write it down. We had lag 1 with lots of values, right? Maybe it starts from 112 all the way to 600, I don't know. And we had lag 2. Again, because these are coming from the same variable, probably the range is the same, 112 to 600-ish. I'm just speculating those numbers, right? And then, so we're going to sort it for each feature. So here we have feature 1, feature 2, and evaluate every possible split. So we're going to see a histogram like this. This is actually from Python. This is a histogram of lag 1, right? And then we're going to, again, evaluate every possible split. So the data obviously is pre-sorted to expedite the splitting evaluation, right? And this is what we did. The advantage is that it is very simple and accurate. Why is it accurate? Because it's going to consider all the combination. And exactly for that matter, that's the disadvantage of that. It's going to be computationally intensive. So here, again, we had, I don't know, each feature had only, I don't know, maybe 200 possibilities. But what if you have millions of those values, right? So that's why this then this pre-sorted naive is not going to be the best fit for, it's not going to be the most efficient way of sampling data. It's not going to be the fastest. And by the way, this is what decision tree, a simple decision tree and random forest are using for sampling. Okay, the next one is histogram based. So we already have a histogram of features. So for example, this is lag 1, histogram of lag 1, and then we're going to bin those continuous feature values into discrete intervals, right? So I don't know, then this means that instead of 200 possibilities, if the bins are something like this, we're going to get quite fewer than that, right? So maybe we're going to end up with 20 of them, right? Basically, the idea is to reduce the number of potential split points. What is the advantage? It's going to reduce computational load, but what is the disadvantage? There's a trade-off, right? You may miss optimal split within bins. So that's why, again, there's always pros and cons. And this splitting method, this sampling method is what XGboost is using. So XGboost, I'm going to write it down, XGboost. We're going to see all these things in a nice table at the end of the day. XGboost is using histogram based, and then Catboost is going to use a different way. It's going to bin the data, but it has its own specific feature binning. So I will talk about it briefly when I introduce it. All right, the last one is GOSS, right? Which stands for gradient-based one-sided sampling. So I'll tell you what do I mean by one-sided sampling. But basically, this is for the models that are basically gradient, based on gradient boosting methodologies. So that simply means that the LightGBM is using this one because it's a gradient boosting. The idea is pretty straightforward. So this is going to focus on samples with large gradients, right? Remember, guys, there's an objective function here. So for example, we have mean squared error. So you can calculate the gradient for each observation, the gradient at each observation, right? And those observations with the higher gradients, those are basically higher errors, those are going to be problematic down the road. So we want to focus on them more and undersample the ones with the smaller gradients. So that's why we call it one-sided, because it's going to oversample one side versus the other one. And of course, it's going to adjust the weights based on those gradients accordingly. So what is the advantage? It's going to reduce computational cost. And what is the disadvantage? Because we're undersampling from the smaller gradient ones. What is the disadvantage? It's more complex. But anyways, it's going to be more efficient and faster, so that's why LightGBM is using it. So this was the second question, how to sample the data for splitting. And now you know that each method is using what kind of sampling method. Each model is using what kind of sampling method. Now, moving forward with the third question, how to split the samples. Remember, this is the question, what features in cutoff to start with, right? So this is a splitting question. And there are two methods in general, greedy and non-greedy. So I'm going to tell you upfront, all the decision tree based models that we cover are going to be greedy. So your decision tree, your random forest, your XGboost, your Catboost and LightGBM, they're all greedy. What does greedy mean? Greedy means that, remember, at each node, we needed to select the feature and cutoff that provide the max information gain. For regression analysis, what was the max information gain? It was the greatest, the largest reduction in the loss function. Which cutoff give me the smallest total mean squared error? Do you remember we had different regions? We needed to add them up. Which split is going to give the smallest summation of those mean squared errors, right? So, and these decisions are made based solely on local optimization. So this is where the term greedy is coming. So without considering the feature splits, at each point in your decision tree, you're going to say, what does this cutoff, what does this split is going to do for that level? You're not going to look ahead and optimize the global thing. This is local optimization. Again, that's why we call it a greedy algorithm. What is the advantage? It's simple and computationally efficient. And what is the disadvantage? Of course, you may end up in a local optimal, right? So you're not going to get the global optimal tree. But remember, all the methods that we cover in this module are going to be greedy. This is a standard method for splitting the data using a decision tree. What is the non-greedy one though? So non-greedy one obviously is going to do some optimization, right? It's going to consider global impact of splits, not just for that specific point in the tree, right? It's going to do that by evaluating future nodes. So that's the key term. Future nodes or using global optimization techniques, right? So we have methods like look ahead splits, evolutionary algorithm, Bayesian trees, and etc. But the idea is that they want to look at the entire aftermath of that split down the tree and then to come up with the optimization for that. So obviously it is more accurate and generalizable by avoiding local optimal. But the problem is that it's going to be computationally expensive, right? Because it's more complex. All right, the next big question is how to grow a tree. Basically, if you're going down a tree, how do you decide if should you go one way or you should go both ways, or should you be symmetric? What is the answer, right? So obviously there are three methods, so depth-wise or level-wise, leaf-wise, and symmetric. And it's pretty straightforward. Let me walk you through an example and intuition. So the depth-wise, as the name suggests, or level-wise, as the name suggests, this strategy grows the tree level by level. So exactly what I did. So start from here, I go to level 1. When I go to level 2, I don't stop here. I complete it. When I go to level 3, I go all the way. I don't stop here. I go all the way, right? So this is the level by level, and we do it one level at a time. All nodes are expanded simultaneously before moving to the next level. So this is exactly what I did, right? What is the implication? This results in a balanced tree structure. So that's what you're going to see. We start from here, then here, then here, and etc. Okay. The next one is leaf-wise. So how does leaf-wise do the job? This is strategy, rather than growing by levels, it focuses on expanding the trees by adding nodes to the leaves, right? Especially those that results in the highest decrease in impurity, or in our case, highest increase in information gain or decrease in the mean squared error, right? The summation. So let me show you what does it mean. It says that if I go to the level 1, but I want to go to the level 2, then I don't need to complete this part. I can go to level 3. I can go to level 4, something like that, right? So this can lead to an unbalanced tree, but potentially more efficient one. So this is what LightGBM is using, so that's why it's faster and more efficient. And here is, schematic version of that. And lastly, the symmetric. So symmetric on the surface looks pretty much the same as depth-wise, but let me walk you through the difference. Again, this strategy attempts to maintain balance not just in the depth of the tree, but also in how the features are split. So basically, it's going to be symmetric on splitting as well. So what I want you to pay attention is this. So look at that. Imagine we start from here, and in our example, the split was lag 1 less than 300. And then, so imagine this was your lag 1, lag 1 less than 300. Then the second split, this is lag, again, 1 less than 400. And if that's less than 400, well, they're going to be exactly the same, right? So this one is going to be, well, I have to go with something that makes sense here. So here, because both of them are the same features, it doesn't make that much sense. Maybe I go with lag 2. But whatever it is on the right-hand side, this is going to be exactly the same on the left-hand side, lag 2 less than 400. So that's the difference between symmetric and depth-wise. Again, it's going to go down the tree very symmetrically, and then it has to do level by level. But the difference is that, look at this, these two are exactly the same criteria. Whatever, lag 2 less than something, x1 greater than something, x3, both of them are the same. But here, in the depth-wise, they were different. They could be different, right? So for example, one of them is lag 1, one of them is lag 2, one of them is feature 1, one of them is feature 2, and etc. So that's the difference between the symmetric and depth-wise. For all these algorithms, for all these methods, they repeatedly split the data along the feature with the highest information gain. Again, in this case, maximum reduction in some of the mean squared errors, until there's a stopping criteria, right? That is stopping criteria, and this applies to any kind of decision tree-based models. It can be max depth, minimum number of samples at terminal nodes, and etc., etc. And finally, the last question is how we combine these trees. Obviously, this applies to the models that involve more than one tree. So basically not a decision tree. It can be bagging, it can be random forest, XGboost, Catboost, or LightGBM, right? So there are two general ways of combining these trees. One is bagging, the other one is boosting. And probably you have seen something like this before, but I'm going to review it very quickly for you. So what is bagging? The idea of bagging, imagine guys, this is your original data set, right? This green data set. Bagging consists of creating many copies of the training data at the same time. So each copy is slightly different from each other. So because these are random sampling, right? So this is copy number 1. And again, they're slightly different from each other, right? And then we're going to apply a weak learner in this case. Our weak learner is a simple decision tree to each copy to obtain multiple weak models and combine them, right? So this is going to be your decision tree number 1, decision tree number 2, decision tree number 3, and each of them are going to give you a y hat. So y hat 1, y hat 2, y hat 3, right? You get the idea. And of course, at the end of the day, this is the average. So we take the average, and that's how the bagging is going to work. And this is going to be done in parallel, right? So that means that these trees that we're talking about, they are independent from each other. Again, the process, this bootstrap, these trees are independent from each other, right? So this is the idea of bagging. So your random forest is an example of bagging. And yeah, basically the bagging decision trees and random forest, these are two decision tree based models that are using bagging methodology. The other one is boosting. So what is boosting? Again, you have your data set. You're going to work with the relatively the original data frame, and then you pass it to a weak learner. So this is going to be your decision tree number 1, right? Again, we're going to iteratively create multiple models by using a weak learner. Each new model tries to fix the errors which previous models make. So your decision tree number 1 is going to give you some prediction, right? And then whatever was not able to explain is going to pass it as a residual to the next. So this data set, the target variable is going to be residual. So here's decision tree number 2 is going to give you a prediction for that residual, and etc. So at the end of the day, obviously the summation aggregation is what? The aggregation is a weighted average of all these things, right? And obviously the bigger chunk is going to be the first 3. There you go. So however, in boosting, each tree is grown using information from previous trees. So these are not independent from each other. So basically, we are passing the residual to the next tree to make it better, to make it better, to make it better. All right. And obviously, the Catboost, LightGBM, and XGboost are using boosting methods. Random forest and bagging are using bagging methods. All right. That was pretty much it, I guess. Now, let's summarize everything we covered so far in this one nice table. So maybe this is a takeaway from this whole lecture. So on the left, I have, all these 4 questions, sampling process, splitting method, tree growth strategy, and combining trees. And on top, we have decision tree, random forest, XGboost, Catboost, and LightGBM. So let's go through them one by one. So in terms of sampling process, decision tree and random forest are doing naive. So we talked about what is this naive and how it works. Basically, we're going to consider every single combination of the available splits, right, at each value. XGboost is using histogram base, Catboost is using feature binning, and LightGBM is using GOSS, right? So again, I promised you to explain the difference between histogram base and feature binning. So or quantization we call it. Let's talk about it here. So at a high level, they're pretty much the same. They're binning the data, but the formation is different. In histogram base, basically the idea is that those histograms are built and updated during the training process. So these beans are dynamic. It means that beans can vary between different nodes and in iterations that we're going down the tree, right? This adapts to the local data distribution better. However, for feature binning, the way that we're going to create quantize, this beans is basically it's predetermined. Pre-training, these beans are already determined, right? This means that we are going to deal with fixed beans. Now, once features are quantized, the beans remain fixed throughout the training process, right? So that's the main difference. So we have, imagine, I don't know. So this is going to be a lot faster and more efficient because imagine your lag variable is taking some numbers from 112 to 600, right? You're going to say we're going to work with 10 bins no matter what. But here, this depends, right? At each node, we're going to make change. The number of beans are going to change. The width of the bean, everything is going to change here compared to Catboost, compared to feature binning, which everything is predetermined. Pre-training, these things is fixed, but for histogram based during training, those numbers are going to be figured out. So that was the difference. Then, in terms of a splitting method, as I told you earlier, they're all greedy. For growth strategy, decision trees is depth-wise, random forest depth-wise, XGboost depth-wise, and they added leaf-wise as well. This was a newer addition to XGboost. And then Catboost is doing symmetric, LightGBM is using leaf-wise. Finally, in terms of combining tree, for decision tree, it doesn't make sense. For random forest, we're doing bagging. For XGboost, we're doing boosting, Catboost and LightGBM. As the name suggests, we're doing boosting. All right, so that was pretty much it about the theory part of this lecture video. So in the next half, I'm going to walk you through the Python part, that we quickly review that simple example for decision trees, applied to airline passenger data. We're going to play around with the depth number, we look at 2 and 10, but I want us to focus on forecasting, because as you saw in the train set, even a simple decision tree with 10 with depth is equal to 10 was killing it. But we're going to see what's going to happen when we go to the forecasting into the future. Let's say we want to forecast 12 months into the future. And you will see that these models, at least the decision tree models, is not going to be able to handle it. And I'll talk about the caveats and how we can fix them. And this is going to be a perfect segue for us to move forward to the next lecture video, which is the challenges of machine learning in time series analysis. All right, now let's do the Python part. So here is where you can find it. Go to my GitHub account, deep forecasting, and then lectures and codes, module 5. This is the notebook, module 5, decision tree intuition. So this is what we're going to go over. Let me see. You can open it in Google Colab. The link should work. Let me just double check. Yeah, the link works, but I'm going to do it on my local computer. I'm using VS Code. So I have created my own environment, deep forecasting, and there I have PyCaret installed, stats model, and everything required for the econometrics and machine learning section of the course, as you know. All right, so let's go ahead. And again, guys, the goal is to show you how we can replicate. Let me bring the slides. How we can replicate these things, okay? And then talk about the forecasting part. All right, let me go back because I need this slide as well. Let me get to the one step ahead forecast. Okay, cool. So we're gonna go ahead and import the libraries, and this is a data set, airline passenger data. We're gonna go ahead and create 2 lags, lag 1 and lag 2. Remember, this is how we transform our univariate time series data set into a supervised data set for machine learning task, right? And you're going to drop an A's because obviously if I have 2 lags, I'm going to lose 2 observations, and etc. So this is the new data set, right? Then I'm going to go ahead and show you the plot. And obviously, guys, the code, I'm not going to walk you through every single line of code. I expect that at this time you are an expert in doing these basic things in Python. But feel free to pause the video, use large language models like ChatGPT to help you with understanding the details of the code, okay? But the goal of this course in general is to help you to grasp the theory part more deeply compared to application. Because as I have said multiple times by now, down the road, application is going to become smoother, easier, and basically more general down. Okay, so this is our airline passenger data set, and now I'm going to plot lag 1 versus lag 2. This is pretty straightforward. We have basically the lag 1, I put it on X variable, lag 2, I put it on Y variable, and I color code it, right? And so this is, we're going to use this CMap for color coding it, and as you see, the color is basically the values of the target variable, right? So this is what we saw, and then we wanted to see, okay, where to put what feature to start with, where to put the split, and etc. Right? So let me actually bring those slides quickly. There you go. So this is where we are, right? Now, we're going to go ahead and do these models from scratch. And by scratch, I mean using scikit-learn, right? So we're not doing it from scratch, right? It's neither PyCaret, which is semi-automatic, nor doing everything from scratch. This is scikit-learn. So this is the go-to library that everyone uses for machine learning. And I want you to learn it both ways. I want you to learn all these machine learning analysis when it comes to time series, both using scikit-learn and PyCaret. And I'll show you in the next, I think in part 4, when we're going over the Python part in details, I'll show you how you can replicate PyCaret time series regression using scikit-learn yourself. Okay. So yeah, from scikit-learn decision tree, we're gonna import decision tree regressor, and I'm gonna import plot tree to plot it as well. My feature, again, this is machine learning, right? So you have to pass X and Y, the feature and target variable, are lag 1 and 2. So let's go ahead and do that. Then let's go ahead and train the model. I'm not going to split the model into train and test. So this is just in the train set fit, and we're going to forecast into the future. So that's something different, right? So we are going to start with the max depth is equal to 2, right? So decision tree regressor max depth is equal to 2. We're gonna fit the model using the data X and Y, and then add it to our data set, right? So if I go ahead and show you the head of the data, so data head. So this is what we have so far. So we have passengers, lag 1, lag 2, and these are the predictions, okay? Then I can plot this decision tree, and this is actually what we saw on the slides, right? So this is where these splits are coming from. It seems that the algorithm decided to start with lag 1 and then go to the left route, again lag 1, pick up the split, and now hopefully you have a very clear understanding how the decision tree is doing the job, right? What is the optimization behind the scene and what are the steps? Okay. Then we can go ahead and plot those splits as well, right? So I'm going to do it manually. I'm going to add a vertical line, different colors, and this is basically what this part of the code is doing. Again, the goal is to replicate that. Now we're going to plot those predictions on top of the actual data, right? The blue one is actual data. The orange one, which obviously there are only 4 numbers, these 4 numbers, are the predictions, right? So let's go ahead and do that. So again, we're doing it on top of each other, right? So one is passenger, the other plot is just the predictions. That's simple. This is pretty straightforward. And as you can see, the max depth is equal to 2. Now, if I go ahead and go back and increase the depth is equal to 10, what do you see? So let's go ahead and do this fun exercise. Obviously, this tree is going to become a lot bushier. At most, we can have 2 to the power of 10 of terminal nodes. This is the maximum, right? And then 2 to the power of 10, this means that we can have literally 2 to the power of 10 predictions. So that's why it's going to cover everything, right? So let's go ahead and quickly do that. I'm going to change this max depth to 10. So again, this one is going to become super busy. Maybe I should have, a lot bushier. Of course, there's as I said, the max is 2 to the power of 10. There is a stopping criteria, and it seems that the depth of the tree, we can check for the depth of the tree, which I think we set it for 10, right? Is 10. Then, we can, well, obviously I don't want to plot this part. This is going to become irrelevant here when the depth is equal to 10. But this one is going to be interesting. Look at that. When I run this, it's literally memorizing everything. So this is, I don't want you to get super excited. You know, decision tree based models like random forest, they are perfect for overfitting, especially in the train set, right? They're really good to basically bring down the mean squared error to almost 0. And this is what's going on in the train set. And we're going to see when we focus on forecasting, what things are breaking down and what are the solutions, right? So that's it. This is if the max depth is equal to 10, and now you are able to replicate these slides. Okay. Now the rest, I want to focus on forecasting part, right? Because as I promised, this is going to be a good segue to part 3, which I want to talk about the challenges of time series machine learning. So let's go ahead and do that. Okay. So I'm going to go back and then reverse it into max depth is equal to 2 because we're going to need it later on. Okay. So now we can see. And then, let's go ahead and create a couple of other machine learning models, and then move to the forecasting part. And by the way, guys, this is, you can import any kind of machine learning model. So for example, I can do from scalar, linear models, I can do linear regression, right? I can do k-nearest neighbors regression. I can do SVM. I can do whatever. So this is, when I said that in the lecture video that you're just changing the engine, this is what I mean. Just simply replace this random forest regressor with linear regression, with KNN regressor, with SVM regressor or SVR, right? So then you get a new machine learning models, but the data is the same data. You're going to apply it. You get different predictions. That's simple. Okay. So that's why I just assume that you have some background in machine learning and you can apply it easily in Python. Okay, so let's go ahead and train this random forest model. Now I call it RF underscore model. The previous one was DT, decision tree underscore model. So we're gonna look at them. Actually, now we're gonna add the predictions of this random forest model to the data, a new column called random forest predictions. So this is what we have so far. So again, pretty straightforward, target variable x1, x2, this is what decision tree predicted. Obviously depth is equal to 2, that's why all these numbers are the same. Random forest, depth is a lot bigger. We're gonna look at the number of depth and then you will see what was the depth and how we can have different values here. All right, so I can go ahead and plot the predictions of random forest. It's doing an okay job. But before I move forward, I want you to pause the video and think about this very fundamental deep question. So I said, wait a second, the random forest is underperforming just one single tree with depth is equal to 10. What is going on here? At least in the train set. You following? So remember, if I had a decision tree with simple one decision tree with depth is equal to 10, what do we get? We get something like perfect fit in the train set, right? Like this. But compare this one with a random forest, which is supposedly more complex model, but still it's underperforming in the train set. So what's going on here? So I give you a hint. I say go back and turn off the bootstrap. So this is a very subtle point. I want you to bear with me and then understand it very clearly, because this is the part that many practitioners out there just blindly use random forest from scikit-learn without taking into account that, hey, this bootstrapping is just shuffling the data. So what's going on? So I'm gonna go ahead, go back and then turn this bootstrap off. Again, by default, it's on. I'm going to switch it off. What is bootstrap? This is repeated sampling with replacement, right? What is the goal? The goal is to create, let's say, 100 trees, using bootstrap version of the data. But what's happening under the hood, if the bootstrap is true, basically it's going to shuffle the data. So let me show you something. And we're only having 2 lags, right? So imagine this is your data, right? And with 2 lags, if it shuffles the data, so maybe y1, y2, y3, y4 is at the top. Again, we have 2 lags. You can maybe focus on the first 2 columns. And then maybe y5 and y6 are here. y10 and y11 are here. And then y2 and y3 are. So as you can see, it's shuffling. So between observations, we are losing the temporal information. Again, I repeat myself. Between observations, we are losing temporal information. Within each observation, there is still some notion of temporal information because I have 2 lags. So I have y1, y2, y2, y3, y8, y9, right? So within observation, there is some temporal, and if I increase the number of lags, that might help. But between observations, if I shuffle the data, I'm completely losing that temporal information. So that was the problem here. Again, there are ways to fix it. And one way is to just stick with the level data like airline passenger and switch off the bootstrap. This is the minimum I expect you to do. And more professionally, we can make the data set, we can make it from non-stationary to stationary and then shuffle the data with more trust, right? It's less concerning if the data set is stationary compared to non-stationary. I'll talk about all these things, just bear with me, but this is a very subtle point. So I'm gonna go ahead and run this. Now the predictions obviously are gonna change, and there you go. So your random forest without bootstrap basically is doing a perfect job. So hopefully you're appreciating how important it is, at least in the train set. Again, this is the minimum. This is a minimum that your model should be able to do. Your model should be able to overfit in the train set. If not, then it's not complex enough. So by simply switching that bootstrap to false, we were able to achieve that. But in practice, this is not necessarily the best way. So I'm going to switch it back to true, and I'm going to show you how you can fix that problem. Especially, these are problematic when we get to the forecasting part. So that was the random forest. I can go ahead and quickly show you how these things look for the XGboost and then move to forecasting part. But before that, look at that. We can check the depth of the tree. So here is 11. So again, in this random forest, the depth was 11. So that's why we get something like this. Then guys, remember, this is machine learning. We're losing interpretability, but we can still have some sort of interpretability, right? Remember, we said that we have, there you go. Interpretability, it's moderate, right? We can have feature importance. So what is feature importance? It says that between lag 1 and lag 2, between feature 1 feature 2, which one was most relevant? So obviously lag 1 was the most relevant. Most relevant here, what does it mean? It means that this is the magnitude of the reduction in the total mean squared error. So that's how, if you want to interpret it. You cannot necessarily quantify, make a quantitative statement about it, but relatively speaking, you can see that lag 1 is a lot more important than lag 2 for this model. Okay. So we're going to repeat this exercise using XGboost with 100 trees, and this is an example of boosting, right? So random forest was example of bagging. This is example of boosting. Again, the process is pretty much straightforward. I already have XGboost installed. If you install PyCaret, the full version, XGboost comes with that. And Catboost, LightGBM, they all come with that. So you can go ahead, simply run it. And if you want to avoid the headache, you can just run everything on Google Colab and then just do pip install PyCaret full. All right, so this is the third column for prediction, XGboost predictions, and then as always, we can visualize it. And as you see, XGboost is killing it in the train set, right? So it seems that in the train set, we have decent models. Even the decision tree with depth is equal to 10 is doing the job. A random forest switching off the bootstrap is doing the job. Again, if you want to forecast the levels. And an XGboost is doing the job in the train set. So we're super excited. Let's see how do these things perform in the forecasting horizon, right? Again, just like random forest, we can look at the depth of the tree for XGboost. As you see, this is super bushy, 120. And we can do feature importance for XGboost as well. Not surprisingly, lag 1 was more important. All right, so now let's focus on forecasting into the future. So this is going to be super exciting and super important, so bear with me. Okay, so let's talk about forecasting. And I'm gonna focus on the simplest version of forecasting, one step ahead, and then basically we're gonna do single output. Let me see if I can, yeah, there you go. I'm going to do single output, one step ahead and multiple step ahead because I want to forecast it into the future. And then we're going to save this idea of how we can do multi-output predictions for the detailed lecture video when I do in part 4. Okay, so far, what do we have inside this data set? Again, passenger data, this is Y, X, predictions for decision tree, random forest, XGboost, right? And we know that they do a decent job in the train set. Now I'm going to go ahead and define a function to forecast into the future. For example, I want to forecast 36 months into the future. Okay, so I will create this forecast future function. And guys, don't get stuck in this function. Don't get overwhelmed. This is pretty straightforward. Pause the video. I'll walk you through the logic, but if you think that you need more explanation, just ask ChatGPT, copy paste it, and then even in Gemini, GPT, Claude, Grok, whatever you have access, depending on what country you're logging in from. But the idea is that just copy this one, paste it there, and say, hey, explain this code line by line to me. And then hopefully it helps you to understand and to understand things better and solidify your coding. Okay. But what is it? This is a function that I'm defining. Say, give me your machine learning model, which has been trained, and then give me the data and how many steps into the future. Well, the machine learning model that you're going to basically use for prediction, right? And how many steps into the future you want to use, right? So then, off of that data, I'm going to create the lag variables. Of course, we can make it a lot more customized. We can say, and later on, I'm going to do it actually. I'm going to make this function a lot more customizable. You can set the number of lags. You can pick up any different machine learning models. But here, just for the sake of argument, keep things simple. I assume that you're working with pre-trained models. Yeah. Then what are these things? These are future predictions. It's an empty list and basically a placeholder. We're going to fill them in. And we're going to, guys, what we're doing here is this. Multi-step multi-step ahead predictions, right? So I need to pass the first two observations. So imagine, so here we're using 4 lags, but imagine this is 2 lags. So I need to use 2 lags and then make the first prediction. So this is what we're doing. And we're going to do it iteratively, right? So I'm going to put it in a for loop and say, hey, do this, right? These are the steps. And let me see, steps, we said 36, right? So do this thing 36 times. The data frame is lag 1, lag 2. So this is the input data, and then this is just in terms of for naming them, I call them lag 1, lag 2, because later on we need them. And then this, look at that, next predicted value. This is your y hat. This is your kind of reddish prediction, right? And we're going to use the model, say predict, use these 2 information, lag 1, lag 2, and then give me the first prediction. Basically, it's going to be this one, and save it here. So this is the next value prediction, right? Then I need to update it, right? I need to use this one. So this used to be lag 2, lag 1 prediction. And now this needs to be, I need to update them, right? So I need to say, hey, the lag 1 is going to, lag 2, look at that, it's going to become lag 1. Well, actually, the previous lag 1 is going to become the new lag 2. And the previous forecast is going to become new lag 1. So I'm just rolling this thing, right? And then I'm going to append all those next value predictions into the future prediction list, empty list. Again, this should be pretty straightforward, but if you have any questions, leave a comment and then I'll try to answer that. Okay, then, yeah, so we have a function here. This function is waiting for a pre-trained model. I have RF underscore model, I have DT underscore model, I have XGboost underscore model. I can use any of them. Pass the data, how many steps into the future you want to forecast. And yeah, so basically, and then here I'm just using data range from pandas data frame to make sure that the number of month is just lining up when I want to forecast into the future, right? This is just a placeholder for the index. Okay, so let's go ahead and visualize it. You ready? Oops. So what's going on here? And it seems that in the train set, actually the model was able to capture the trend and seasonality. In the test set, or you can say forecasting, right? This is not test set. This is something that we haven't seen, right? This is into the future. For the next 36 months, the model is doing something like this, right? And then again, I can go ahead and change this. Yeah, I have to change the labels as well. But I want to show you one of them. For example, if I change it to DT, ignore the labels. The labels are going to be still random forest, but this is going to be your decision tree, which is doing an awful job into the future, right? Again, this is the decision tree with just depth is equal to 2. So if I do XGboost, we get another thing, XG. What did we call it? Did we call it XGB? XGB. Let me see. XGboost model. Okay, call it XGboost model. And then this is how things are going to look like for XGboost, right? Again, ignore the label. I need to change the labels, but this is what your XGboost is doing. But you get the idea. Neither of them or none of them is capturing your trend. So RF. So let's see. What was it? Yeah, RF model. Yeah. Okay. So then this is, we need to pause here for a second and talk about a very important stuff which is going on, right? So I have written down everything for you, but I'm just going to quickly walk you through that. So what's going on when we are predicting to the future for 36 months, why these models that were seemingly doing okay in the train set are not doing good in forecasting into the future? So what's going on? There are multiple things going on here. The first one is, I call it lack of explicit trend and seasonality modeling. Remember guys, in econometrics, we explicitly modeled, let me bring that, there we go. We explicitly modeled the trend and seasonality. For example, in ETS, you add level, trend, and seasonality components. In ARIMA, you you integrated the data, you differenced the data, so that took care of the trend part, right? But in decision tree here, we're not doing anything fancy. We're just using lags and that's it. And it seems that it's not cutting it for forecasting into the future, right? So that's one problem. Another problem is recursive forecasting limitation. So remember guys, what we're doing here is this. So these green ones are already previous forecasts. So these errors are going to add up. And because the cards in general, decision tree based models are not specifically modeling the trend and seasonality, this error is going to become bigger and bigger and bigger, right? So that's basically, it's going to add up to the worst performance as we increase the time horizon. And then the third one is feature representation. Again, we didn't do anything fancy here. We just use a bunch of number of features here. Okay, so for random forest, I think we are only using 2 features for this specific example, lag 1, lag 2. So that's probably not enough to capture the nuance in the data. And remember, if I include more lags, so that within observation, again, not between, within observation, there's going to be some notion of temporal information, right? So let me actually tell you what I'm talking about here. If I only have 2 lags, so for each observation is looking into 2 consecutive numbers. If I do 4, it's 4. If I do 12, so it's 1 year of data in one observation, right? If it is monthly data. So then I can say within each observation, there's some appreciation of the time information there, right? So that might be one solution. One solution might be, you know what, go ahead and increase the number of lags, right? And yeah. So that's the feature engineering part. And what else we could do, we could probably use more time related features like, rolling averages, time indicators for seasonality and things like that. So these are the solutions, right? How we can get better forecasts. And lastly, which is also very important, is the stationarity assumption. So many machine learning models, including this decision tree based, perform best when the input data is stationary, meaning it has a constant statistical properties over time. So this data set is obviously non-stationary because there's a clear trend and seasonality. And then the idea is that, okay, what if we make it stationary first? Then we know that the statistical properties are going to be constant, the average, the variance are going to be constant. And then maybe we can model that stationary data, make predictions, and then add back trend and seasonality. So that's also another solution. I'm going to talk about this stationarity in the next video in more details. Then to tell you what are even with what kind of data sets are still challenging for machine learning to handle it, right? Because stationarity, we can have severe form of non-stationarity or simple form of non-stationarity. So for example, airline passenger data, this is non-stationary, but the data is well behaved. Stock price data, it is not stationary, but the data is not well behaved, right? So, and machine learning models are going to treat them differently, right? Okay, so these are the problems. What are the solutions? As I said, we can do more detailed feature engineering. We can increase the lag numbers. And we're going to see, this is my solution number 1. This is not going to cut it if there's a strong trend and seasonality in the data. But another more, again, relevant solution is to transforming the data. We can transform the data, detrend and deseasonalize. Actually, I can go ahead and add data transformation as well. Data transformation plus detrending and deseasonalizing. And this is, guys, this is a pretty standard approach when it comes to doing machine learning for time series. And this is exactly what PyCaret does. PyCaret automatically, before doing any analysis, it's going to pre-process the data for you, and it's going to detrend it and deseasonalize it and make predictions on that stationary data. So when you're using machine learning models with PyCaret, you will see this acronym. So for example, if it is random forest, you will see RF_CDS. So that CDS stands for conditionally deseasonalized and detrended. Okay. So now you know what PyCaret is doing under the hood. So let's consider both of these solutions and see which one performs better. So I'm going to go ahead and start with the first one. I'm going to increase the number of lags. Instead of 2, I'm going to include 12. So with the hope that, yeah, even if I shuffle the data, this within observations, temporal information is not lost because I'm looking at 12 consecutive data no matter what. No matter how I shuffle the data for each observation, because I have 12 lags, the model can see, when I say I mean the model can see 12 lags, right? So let's go with that. So I'm using basically a for loop to create that lag things. So again, this is pretty straightforward. And we are going to go ahead and create that model. So I'm going to go ahead with a simple decision tree regressor. Max step is equal to 20. Train the model. So we can have different models, right? Decision tree model number 2 is the one with 12 lags. Random forest model number 2 is the one with 12 lags, and etc. So this is the new predictions using 12 lags. Okay. Then I'm going to go ahead and forecast with 12 lags now. This is a new function. Basically put everything we did in the previous cells in one cell and then just call it. Again, the logic is pretty much the same. The logic is exactly the same. We're going to roll over those predictions in an iterative way. So this is one step ahead forecast. Okay, multiple step ahead forecast. Okay, so this is our forecast with 12 lags. We're going to do it more systematically in part 4. So you don't need to be worried about the details of the codes here. Just bear with me and understand the intuition. And now I can go ahead and plot the same thing using 12 lags and predict the next. We can do 36 to be consistent with the previous one. 36 month. And I can do it for which model are we using? We are doing random forest, right? As you can see, it seems that it is trying to capture the upward trend, and after 12 months it's having hard time. So it seems that, yeah, including more lags looked promising in the forecasting horizon, but in practice it's not working, right? So either I do decision tree or random forest, you will see that the forecasts are still kind of off, right? It kind of captured the trend a little bit, but it's at some point it's just derailed, and the seasonality it's there, but again after some point it's completely gone. So that's why we're going to stick to the more general and more appropriate solution for this problem, which is transforming the data, detrending, and deseasonalizing, right? And this is exactly what PyCaret does under the hood, and any other decent time series forecasting Python packages like SKTime, PyCaret, NixTLA, you name it. Okay, so I'm gonna go ahead and import. So we're gonna do random forest, and I'm gonna go ahead and from TSA stats model TSA import seasonal decomposition. So this is a simple ETS decomposition, the STL decomposition, because you want to take out the seasonality and take out the trend and just make predictions on the deseasonalized and detrended data. This is pretty straightforward. I'm going to walk you through this code and then you will feel a lot more confident. So first step, I'm going to do log transformation. So what do we do in log transformation? I'm going to work with log passengers. So this is the first thing I do is to hopefully take care of the variance of the data, right? We know that if we do transformation like this, box-box transformation, log transformation, it will take care of the variance of the data. And that's exactly what we needed, right? So now I don't see this increasing variance in the data. Then, so this is one step. The next step is to go ahead and take this log passenger data, take the trend out, take the seasonality out, okay? So how do we do this? I'm going to create this decomposition object and use seasonal decompose from stats model, pass my target variable, which is log passengers, and I'm going to decompose it in an additive way, right? So we have talked about all these things in the previous module, and the periodicity is 12. So, and then I'm going to save those deseasonalized and detrended data. So deseasonalized is basically, this is deseasonalized and detrended. So say, take your target variable, the log passenger, subtract seasonal, subtract trend. So this is deseasonalized and detrended. So I think a better term, I should have renamed it to deseasonalized, detrended, okay? But I wanted to keep it short. But you get the idea. And then with that, I'm going to create lag 1, lag 2, look at the head of the data. So this is what we're interest set. So this is going to be the new variable of interest, y, these are the target variables, and these are the new features, x1, x2. And I'm going to go ahead and make prediction on these ones. So just in order to show you what we're doing, this decomposition is taking the log passenger, taking the trend out, taking the seasonality, and then this minus this minus this is what's going to, what we're going to model, right? So basically, I can visualize it for you. This is what we're going to apply random forest or decision tree based models to make forecasts on this. And as you can see, this is a lot more stationary. And the mean is going to be constant over the 36 month into the future. The variance is going to be constant, and etc. Right? So now what I'm going to do is to make a prediction on this data frame or in this time series. And after that, I'm going to add back the trend component and the seasonality component to get back to the predictions. Okay, so let's see. Again, this is what we have so far. And let's see. So the features, as I said, are lag 1, lag 2, and the target variable is deseasonalized. Remember, this is deseasonalized, detrended. So I'm gonna use a random forest model with bootstrap false. I'll try to do it correctly, right? And number of estimators 100. Honestly, here, because this is the data is stationary, it's not gonna make a huge difference if I switch this on or off. So you can go ahead and give it a try. And then I'm going to make some predictions. So this, look at that, random forest underscore DT, detrended underscore deseasonalized. This is something you're going to see in PyCaret. So PyCaret is going to use some notations like this. Make predictions, and these are your predictions, right? After I made predictions, I'm going to add back the trend components and add back the seasonality components. Hopefully this makes sense. Again, it should be pretty straightforward. And these are going to be our new predictions. And I have the actuals, log passengers. I have the predictions. Let's plot them. In the terrain set, it's doing an awesome job. Now the goal is to see how it performs into the future, right? Because we already saw that without detrending, deseasonalizing, only adding more lags, it didn't cut it. So let's see if this new solution works. So again, I'm going to put everything in a nice function. And I'm confident that this model is going to work. I'm going to forecast 100 months into the future, which is crazy, right? And then I'll create my own forecast future. This is deseasonalized or detrended. You need to pass the model, data, decomposition, and how many time steps you want to forecast into the future. By default, it's 36, but I think we're passing 100. Again, feel free to pause the video, go through these things. This is pretty straightforward, but the point of this lecture video is not to get stuck in the Python part. But again, let me know if you have any questions. But other than that, just let's go ahead and create this function. And let's run it. Forecast futures, deseasonalized or detrended. This is the model that we trained. This is the data. This is the decomposition we're using. Again, we use the stats model for decomposition. And that's it. Basically, we put everything in one nice cell. So now let's look at the predictions into the future. Voila, it's working. It's working greatly. Okay, so as you saw, our econometric model ETS and ARIMA was easily able to make a nice prediction like this. But our machine learning model was not that straightforward, right? So that's why I'm really wanting you to pay attention. You cannot blindly use scikit-learn, for example, import SVR or KNN or I don't know, the fancier models, XGboost, random forest from scikit-learn, and then apply it to your time series, and you think that it's going to do a good job for forecasting. So that's what I want you to take away from this lecture, and these are the challenges. We're going to talk about the details of these challenges in the next lecture video, which let me actually go ahead and show you. This is going to be our part number 3. So we're done with this part 2, and in part 3 we're going to talk about more details about non-stationarity, seasonality, basically the right way of cross-validation and bootstrapping. So hopefully that was helpful, and yeah, we're going to go back to the slides now. Great, that was pretty much it. So far we've covered part 1 and part 2, and in the next part we will talk about the challenges in time series machine learning. Until the next one, take care. If you're looking to stay updated with the latest versions of the course's materials, please make sure to follow my GitHub and remember to refresh your repositories periodically. If you find yourself needing a bit more background in econometrics, machine learning, or deep learning, check out my other YouTube videos for additional insights. And for all the latest news and quick updates, don't forget to follow me on Twitter. Thanks for joining me, and let's keep learning together.